Oh, hello there. I guess what's going on? Memes here. Yes, it's late. It's a Friday. What better time to put something out there that people can completely ignore? I know. I'm saying this full disclosure. Paradigm Drift is it's going to be a recording where again Shiloh and Anastasia from the DemystifySci folks uh basically pull names out of a hat. If you happen to get pulled and you are available and can coherently and have the technical, basically as long as people can hear and see you, you have an opportunity to present your idea. But I know I've been a little absent. I may have been going down a little Wolfram hole, but let's uh, let's see what we have. Um, so there's this whole concept of the spherical cow in physics. I had ChatGPT make the little cute little cow image. So let's take a look at it. Why am I talking about a spherical cow? Because there's no such thing as a spherical cow. What it is within the realm of physics, it is an idealized situation, i.e., we're assuming optimal conditions because, well, very often if you're experimenting, you need to account for an infinite number of variables and stuff. And at least that's what I was taught when I was starting to go through science in high school, chemistry, physics, all that stuff. You account for as much stuff as you can, the best way you can. Yes, welcome, Poindexter. I think you guys are gonna like this. So, yes, we have our spherical cow, even though it's not quite spherical, but it's adorable there. And the title of the stream is The Cosmological Cow. Spherical, that is. Why? There's a little thing down here that you can't really see, but don't worry, we're going to go through it really quickly. We will explore this because every once in a while you go back to different things, and sometimes you get different measurements, and you see things and you see things, and you don't understand things, and then sometimes they kind of... We'll get into it. We'll get into it. It's hard to explain without actually doing it, so let's jump right into it. Okay. So here's that thing. Why do I say cosmological cow? Okay. Because where is it? Where's the best guy to show what's going on here? Okay. So as far as cosmology and stuff goes, let's bring this guy up, share with the class. All right, we get this window over here. All right. The cosmological constant, okay. That thing that people didn't believe exists, and some people... Einstein is allegedly to have said that introducing this term was his biggest blunder because obviously that wasn't how reality was. Future observations, it's like, well, there does seem to kind of be a cosmological constant. Is it changing? What exactly is it? I don't know. I found something that's very interesting. Okay, so the cosmological constant, keywords you'll hear is lambda, which is basically this little up arrow here. The definition, 8 pi, so basically 2 spheres, times big G, the Newtonian gravitational constant, times the universe's vacuum energy density, all divided by C4. Okay, long story short is big G over C4, that's C4 over big G is the Planck force. This is just 8 pi, whatever the vacuum energy density is, divided by the Planck force. Okay, so the key thing to notice right here is it gives you this number. We only have it to so many significant digits because depending on the data set you have there, if you're including supernova that seem to be farther away, the calculation seems to go up to, I think, 0.4 or 1.4, 1.5 times 10 to the minus 52. Incredibly small number. Why might it possibly be the case? Okay. So we're going to highlight a very interesting coinkydink if you take that whole concept of the spherical cow literally. Why do I say this? Okay. So let's start. Let's make a new tab. Okay. So let's take something like Higgs boson. Higgs boson. I'm not even going to use my calculation there because is it right? I don't know. Maybe it is, maybe it isn't. But for just the sake of this argument, you don't need a conjecture that, well, the solution to the hierarchy problem, so to speak, is because why is the Higgs mass so much smaller than the Planck mass? Because it's scaled by the square root of magnitude of h bar Planck's reduced constant. Maybe it's true, maybe it isn't. We're just taking the Higgs boson. Okay, so it's going to give you here. Okay, we want it in giga-electron volts for energy, so we're just going to multiply by c squared. So we got the same thing. It just goes... Higgs boson, mass. There we go. All right. So it's giving you this, our standard 125 GeV, which we have high confidence from CERN and hints at the tevatron between a couple of experiments at CERN there. That basically, yeah, there seems to be something going on there. All right, so we're going to take that. Now, I got the Higgs boson, but how the heck do we relate this to other things? It's just energy. How big is it? Is it Planck scale? Is it this or that? So what if we literally do the noob thing? We do the most naive thing we could. We just... Because the Higgs has something called a Compton wavelength. Any mass or particle, it's got a particular associated Compton wavelength based upon its mass and everything. Okay. So what we'll do is, well, let's take the Higgs, Higgs Compton wavelength. Okay. That's going to give us a length. Now, for those of you that might be curious of what's going on here, okay, so it gives you things, Well, that's interesting, because seeing as it's about, to be fair, I haven't actually even looked at this here. It's about 1 h bar c, Planck constants, that is interesting. That's not what we're talking about. I apologize. Wow, I need to do a whole lot more research. All right. Basically, the long story is we're trying to get a volume. How do you get a volume? Well, you divide something by a cubic length. Let's just take the Higgs Compton wavelength. Let's cube it. Gives us these numbers here. Okay, don't worry. I don't know what those numbers mean either. You got some stuff and things. Okay. But we want it to be spherical, no? AKA the spherical cow, right? Let's treat it literally like a sphere. What do? Well, our standard sphere formula, 4/3 pi. We're using this as our radius cubed, 4 pi r cubed. That's a sphere. Okay. Let's put that in. What do we get? All right, so let's make sure it's interpreting it right. All right, so we got the Higgs boson mass. Massive, what some people refer to as the God particle, whatever that might be. All right. Times the speed of light squared, so we're getting its mass energy. Thank you, Einstein. We got a 4/3 pi, and we've got the Higgs particle's Compton wavelength cubed. So 4/3 pi, a radius cubed. Okay. And we're just dividing it by that. We're taking its mass energy, we're dividing it by what we would naively get as its volume, based upon the Compton wavelength. Okay. Gives you these numbers right here. You're like, means why are you showing me all this random BS? Okay. So if we notice here, hold on, let me open another tab real quick. So let's get some dimensions. So we're taking that crazy number there, and then we're getting, what is it? It's pressure or energy density. Because energy is mass, it would be length squared, and then time to the -2, because that would be division. So what we've done is we've literally divided by a volume. That's why we get this thingy here, because this was length to the third, length squared, because it was energy. We divided it by 3 dimensions of volume. Or 3 dimensions of length, so I just go down to -1. Okay. So there's energy density. Is there some well-known energy density we may be able to reference this to? Okay. How about the universe's vacuum energy density? Universe, vacuum energy density. AKA, some might say this is, what is it, cosmological. One of the problems is, and again, it was an actual prediction, if you assume Planck energy divided by Planck volume, you get the Planck pressure, which is a ginormous, like 10 to the 13 pascals or something. Ginormous number. It's about 122 magnitudes off from the actual 5 times 10 to the minus 10. How could it be so wrong? Why might this be the case? Now, again, there are different... We have this to so many significant digits. It's depending on the data set and everything you pull in there. Yes. Hey, Charlie, I think you're going to like this. So if we just take the vacuum energy density, which is something that we believe to be the case, this seems to be an energy density to the vacuum, aka no true vacuum, perhaps. Okay. Why? Let's conjecture, my friends. So we've got this enormous energy density. We have the vacuum energy density of the universe. Okay. What's the magnitude difference between our measured vacuum energy density to the best of our knowledge and whatever the heck this crazy number gave? Paste, divide. Okay. So we got our observed universe vacuum energy density, and then the spherical cow of what the Higgs energy density would be. Okay. Now again, these are literally just based upon the generic things that are in Wolfram Alpha. You don't need to do any fancy calculations to make all crazy claims or anything. You're just doing the naive thing. Let's look at it. Wait a second. 1.1 times 10 to the minus 52. Wait a second. Why does that number seem so familiar? I don't know. It's cosmological constant. I spelled everything wrong. Oh god. So bad. What? Wait a sec. 1.1 times 10 to the minus 52 reciprocal meter. So it's got inverse meter squared. But 1.1 times 10 to the minus 52. 1.1 times 10 to the minus 52. Why does this have the magnitude of the cosmological constant? That's weird. Long story short is if we take this into it and you can divide it again, but it's kind of, it's weird. It's weird because the cosmological constant does have the vacuum energy density as a term there. So, I mean, if you were to divide it literally by this again, you're kind of double dipping there. And I got confused for a while. So, I mean, in that way, it gives you... What is that? That's... Oh, God. Why is it showing me all those things? So, it's... Is that like tens? Okay. Yeah. So, it basically gives you like 1 square meter. I'm like... When I play around with the toy model that I have there, I'm inserting literally 1 meter or 1 square meter. That ends up being what I have there. This is basically just from the stuff that we normally have here. So going back here, this is essentially what we have. So if you multiply by it, you're going to get the cosmological constant there. Yeah, it's pretty weird. So what is actually going on? The best I can tell about what's going on, let's see, where is that? Is, let's just take what we had. Okay. Let's go back. So, if you notice when we looked at the cosmological constant, if it seems to be giving us that, well, what are the other parameters? Well, 8 pi, this big G and everything. So let's 8 pi big G, so that's just 8 pi over the Planck force. So which gives us, hold on, 8 pi divided by Planck force, aka 1 Einstein kappa, aka the Einstein constant for the speed of light raised to the fourth convention, the C4 convention. Okay. So, what happens? Very, very small number. Very small number. What happens if we do, just multiply this whole thing by the Einstein constant? Now it's going to ask us to verify which one. You got the speed squared. We're going to use the C4 convention here. So the Einstein constant, hold on, let me make sure I have enough brackets there to make sure everything is... Okay, yeah, it's accounted for. All right. Hold on, we need to go to the C4 convention, blah, blah, blah. All right. Result. 1 inverse meter. So when we multiply the Einstein C4 convention times this crazy thing here, and again, it holds for maybe about 2 decimal places because of our uncertainties and stuff, but I'm like, so what you're saying is when we take the C4 convention, we multiply it by that, we basically get 1 in the units of the cosmological constant, except the not ginormous thing. Don't that beat all? I don't know. Okay, I got like 1 minute before paradigm drift. Let me show you one last thing, because I don't think I've really told anyone else of this. Okay, so what happens? Okay. Long story short is, this is the calculation for the Higgs self-coupling constant. What is it? I just threw that number in there just to estimate it. This is basically the number for the vacuum energy expectation. You can get this from Wikipedia. You just put it into Wolfram Alpha. It's the square root of the Higgs mass in energy form divided by the square root of that, and then 2 of them. You get this number. What is that number? When you compute that number, you end up 0.129. It actually comes out with a 4 when you use more significant digits. You just look for a potential closed form, just like that taught me. Well, this seems to get all the digits, and it's a 3. What the hell is Gelfand's constant? Oh, it's e raised to the pi. AKA the principal branch for complex logarithms. And the sum total of all even hyperspheres, apparently. I'm gonna have to go. I'm gonna have to elucidate it on later. I know. Don't have a cow, man. Yes, Rick. I'll got the link below. Anyone wants to pop over, join, and have a chat. I'll be hanging out with those guys. So, other than that, peace out, everybody.